In previous class we have seen what is P class problem, and we have seen an example as well. We have explored the example of Kruskal algorithm for construction of minimal spanning tree, right? And we have proved that it is solvable in polynomial amount of time, and that too can be implemented using a deterministic Turing machine, right? Now in this lecture we are going to cover two topics. One is NP class problems. If you remember, NP class problems are those problems which can be solvable in polynomial amount of time by a non-deterministic Turing machine, right? NP stands for non-deterministic polynomial, right? And we will also see that we have already seen that we can reduce one problem to another using the mapping of the instances, but here we will consider this topic, that is polynomial time reductions. That means we will try to reduce a problem which was supposed to get completed in exponential amount of time. Whether can we reduce it to some problem which is proven to be solvable in polynomial amount of time, right? It is a very useful, it's very useful, if we can reduce one problem which is going to consume exponential amount of time into a polynomial amount of time consuming program, so it will be very helpful for us. We can reduce the complexity by a large range. Okay, now let us begin. Now what is NP problem, or what is non-deterministic polynomial time means? It's a fundamental class of problem in the study of intractability in those problems that can be solved by a non-deterministic Turing machine that runs in polynomial time. As I told you, that here we will use the concept of intractability, means the problems which are intractable, and we will try to solve those problems by implementing it using a non-deterministic Turing machine that can solve my problem in polynomial amount of time, right? So if we have to define this kind of problems formally, it would be like a language L is in the class NP if there is a non-deterministic Turing machine M and a polynomial time complexity Tn such that L is equals to L of M, and when M is given an input of length n, there are no sequences of more than Tn moves of M, right? So that means what? If we are given a problem, or if we are given a language L, we have to design a machine or Turing machine which is going to accept my language in polynomial amount of time, and that Turing machine will be a non-deterministic Turing machine. If we are able to construct a non-deterministic Turing machine which can accept my language L in polynomial amount of time, then we will consider those problems as NP class problem. And previously what we have learned, what are P class problems? If we can develop any Turing machine which is going to accept a language L, and that too can run in polynomial amount of time, and the Turing machine which we have used is a deterministic Turing machine, those problems we considered as P class problem. Fine. Now our first observation is that since every deterministic Turing machine is a non-deterministic Turing machine, that is P is obviously a subset of NP. Means determinism, you can say it's a property of non-determinism only, right? So determinism is a special part within a non-determinism. So here we can say the P is a subset of NP problems, right? Now it appears that NP contains many problems not in P. Obviously there will be several problems which are totally NP class, and we cannot solve those problems in polynomial amount of time by a deterministic Turing machine. We have to go for non-deterministic Turing machine only. So there will be a class of problems there, and the intuitive reason is that a non-deterministic Turing machine running in polynomial amount of time has the ability to guess an exponential number of possible solutions to a problem and check each one in polynomial time in parallel. Why is it so? If you remember, when we move to a non-deterministic concept, if we are given a string of length m, right, So how many choices we could make there? 2 to the power m in case of non-determinism, right? So you can see in parallelly or at the same time it can go for exponential number of moves. 2 to the power m is nothing but exponential factor, right? So it can do it in polynomial. We will see that how each one can be done in polynomial amount of time, right? We will see the proof there, but for now we know that my non-deterministic machines are capable of doing this. Now it is one of the deepest open questions for mathematics whether P is equivalent to NP, that is whether in fact everything that can be done in polynomial amount of time by a NTM can be in fact done by a DTM, right? Okay, this can be we can accept this concept as well, but if you have to map this NTM concept to a DTM concept, and if we have to map it that okay, my this kind of problem my NTM can solve in polynomial amount of time, and if we have to move the same thing or if we have to map the same thing to a deterministic pattern, definitely my polynomial will be of higher degree, right? The degree of polynomial will be higher if we have to map it. Now let us see an example. We will consider our traveling salesman problem. It's a very famous problem. Here a concept of Hamiltonian circuit is there. So you have already learned what Hamiltonian circuit is, what is the traveling salesman problem, and again if we have to recapitulate what a Hamiltonian circuit is, we have to see this, the footer of the slide. You can see there a Hamiltonian circuit is a set of edges that connect the nodes into a single cycle, with each node appearing at exactly once, and the number of edges on the Hamiltonian circuit must be equal to the number of nodes in the graph. So we know how to construct a Hamiltonian circuit from a given graph. So you have to keep these points in our mind to proceed further, right? Now here we will consider the same graph that we have considered in case of Kruskal algorithm for visiting a problem of P class, and here we will use the same graph, and again we are going to consider a constraint on weight, that is W, right? So if we have to depict a Hamiltonian circuit, you can see here the number of vertices are 4, right? So whatever the Hamiltonian path we can design, it can be like see 1 2 4 3 1, and do not means think and do not consider the bold lines here, because the diagram where I have collected the diagram from the previous slide, that's why the minimal spanning tree is shown with the bold line. But here we are going to consider this cycle, that is 1 2 then 4 then 3 then 1. So this is totally completing one cycle, and here we have visited one edge single time, right? We have not covered it more than once. So if we have to consider the weight of this path, it would be like 63. You can see there. Now we have to it would be like if the Hamiltonian circuit is possible for weight is 63 or more, okay, we can draw this with 63 or more, right? We can complete the cycle, but if we have to go for 63, means lesser to 63, it is not possible to draw the Hamiltonian circuit. Now you can see here that if we have to means draw a Hamiltonian circuit where the weight consumption or the total weight of the circuit is lesser, for a 4 node graph you can go for all the choices. You can try, okay, I will start from this one, I can track these paths, I can move to this one, and all the choices is possible. Now if you are given it a graph with m number of vertices, and if m is a large number, is it possible to go for all the choices? No, it's not possible. It would be the distinct number of cycles will go to a factorial, that is m factorial, right? And if we have to and it is a exponential growth. We can represent it like 2 to the power cm. You know, from the concept of algorithm, you can you just derive it, that how order of m factorial we can depict it with more than 2 to the power cm. C is any constant value, so the complexity is going to an exponential factor, right? Now there can be, you can say like this, that okay, I will discard some bad choices. I will not consider this much of choices. I will go for some choices from where I can reduce my number of choices, so the number of trials will be lesser. But how many means how much you can reduce? For a huge number of nodes, you means at the end of the day there will be exponential growth only, right? If we have to discard some bad choices, but the good choices are not so less, means again it will be an exponential growth, right? Now if we have to implement this using a non-deterministic computer, or rather a non-deterministic Turing machine, we could guess a permutation of the nodes and compute the total weight for the cycle of nodes in that order. Okay, so if there were a real computer that was non-deterministic, no branch would use more than order of n steps if the input was of length n, right? Why? Because from one node or from one branch, right, we can go for n number of choices. So if there are total n number of branches possible, so it would the complexity would be order of n square. So you can see that if we are going into a non-deterministic concept, my complexity can be reduced to a polynomial growth, right? It can be done using a multi-step Turing machine. Means since we are going for the parallelism concept, so we need a multi-step Turing machine. In that case, from one we will have n number of choices, from the second we will again have n number of choices. So for total n, there will be n into n number of choices, that is order of n square, right? And again, if we have to simulate this multi-step Turing machine using a single step Turing machine, it will be the square of the whatever the value we have got for multi-step Turing machine, so it will be order of n to the power 4. So we can conclude that my traveling salesman problem is NP, right? That means we can solve traveling salesman problem in polynomial amount of time using a non-deterministic Turing machine. Fine. Okay, now we will see the second topic, that is what is polynomial time reduction, right? Here you can see that okay, for throughout this discussion there will be one capital P, and that capital P means P class problem. Okay, that means the problems that can be solved in polynomial amount of time using a deterministic Turing machine. And for the name of the problems, we will use P1 and P2, right? So here you can see in the diagram there are some instances of P1 which we are feeding to a construct, means the construct with using which we can map the instances of P1 to P2, and we are just feeding the total P2 for decision concept, means whether that is a decidable or not decidable, or what is the time consumption for the decidability. We will see that. So here it is saying that our principal methodology for proving that a problem P cannot be solved in polynomial time, that is P2 is not in P, is a reduction of a problem P1 which is known not to be in P to P2. So we know that if we have to prove that my P2 is cannot be it cannot be solved in polynomial amount of time, so what we generally do in case of this reduction problem, we pick up a problem which is already proven to be non-solvable in polynomial amount of time, and we will try to map the instances of the previously proven problem with a new problem, and if we can map the total concept with the new concept with the old concept and can come up with the same decision, then we can just directly come to the conclusion. So we will proceed accordingly. Now suppose we want to prove the statement, if P2 is in P, then so is P1. We want to prove this. If we can prove that my P2 can be solvable in polynomial amount of time, and since we can map the instances of P2 with P1, that means we can conclude that my P1 is also solvable in polynomial amount of time. Okay, suppose we want to prove this one. Now, since previously, if you consider the previous slide, we have already claimed that P1 is not in P. That means P1 is not solvable in polynomial amount of time. It is means it's a proven concept, right? We know that we have picked up P1 in such a fashion only. Now, then we could claim that P2 is not in P either. So we have claimed this one, but we have to prove that if P2 is in P, then P1 will also be in P, right? That means both of them will be can be solvable in polynomial amount of time. We are going to do that now. Here the construct is not sufficient to prove it, so how to prove that one we will see here. So for instance, suppose that when given an instance of P1 of length m, the algorithm produced an output string of length 2 to the power m. Why? Because we have claimed, or we know, that P1 is not solvable in polynomial amount of time. So we are assuming this kind of fact. That means 2 to the power m means it's an exponential factor, right? So if P1 is given with an instance of, or as a string of length m, then the algorithm is going to produce an output of length 2 to the power m. Now the output of P1, who is going to take it off? P2 is going to take it off, right? So we have fed that 2 to the power m to P2. Fine. Now again we are assuming that you remember that I don't know anything about P2. We have claimed that my P1 is not going to is not a P class problem, or rather a P1 cannot be solved in polynomial amount of time. But if we assume that the decision algorithm ran in time, say it is consuming order of n to the power k, right? Here means P2 can run in n to the power k order of time. That means it's a polynomial growth, right? And on an input of 2 to the power m, from where it has got the input? It has got this input from P1, right? So P2 is having an input of 2 to the power m, and it has been assumed that P2 can run the decision algorithm in n to the power k amount of time, right? So in that case, if it is having an input of 2 to the power m, so the total running or total decision taking will be like 2 to the power km, right? If we multiply this two, it will be like this, because my n factor will be abolished. 2 to the power m is a higher power. That's why we can write the complexity like this. It will be like order of 2 to the power km, right? Now this is an exponential in m. Fine, it's an exponential in m. Now the decision algorithm for P1 takes when an input of length m, that is exponential in m. So we have moved up to this, right? Now these facts are entirely consistent with the situation whether P2 is in P and P1 is not in P. So you can see here beforehand P2 was means coming to with the decision, means it took order of n to the power k for decision making, but whenever we have fed an input from P1, it is showing that it is going to take decision in exponential amount of time. So we can see that P1 is giving an output of exponential growth, but P2 itself is giving a polynomial growth. So we can say that P2 is in P and P1 is not in P for now. Let us proceed. Now, even if the algorithm that constructs a P2 instance from a P1 instance always produce an instance that is polynomial in the size of its input, we can fail to reach our desired conclusion, because we have seen that whenever it is taking an input from P1, it is rising to exponential growth. So we cannot come to our conclusion in this path, right? We have to go for other we have to cover the other way. Now for instance, suppose that the instance of P2 constructed is of the same size m as the P1 instance, but the construction algorithm itself takes a time that is exponential in m, right? You can see here we are doing what? We are feeding the output of P1 to P2, right? And it was of 2 to the power m. Right? So the construction algorithm with which we are trying to map the instance of P2 with that of P1, it is consuming an exponential amount of time, that is 2 to the power m. So if this is so, then a decision algorithm for P2 that takes polynomial amount of time, we previously have assumed it, you can see from the previous slides that itself the decision algorithm of P2 is consuming order of n to the power k. On the input length of n only implies that there is a decision algorithm for P1 that takes time order of 2 to the power m plus m to the power k, right? Why is it so? Because the decision algorithm of P1, it would be like, since the length of the string or the total length is m, so it will be like m to the power k, and 2 to the power m is what? It is the total time taken for constructing the instances of P2 with the help of P1. That's why that 2 will be summed up and it will be 2 to the power m plus m to the power k for problem P1, right? And this running time bound takes into account the fact that we have to perform the translation of P2 as well as solve the resulting of P2 instance. Again, it would be possible for P2 to be in P and P1 not. Again, if we consider this concept as well, so you can see that ultimately P1, what output P1 is generating, it is an exponential factor, but still P2 is having only order of n to the power k. Right, so P2 again is in P class, but P1 is in non-P class. Okay. Now, what should be the restriction? The correct restriction to place on the translation from P1 to P2 is that it requires time that is polynomial in length of its input. So we have to come to this concept. Somehow we have to make the construction algorithm in such a factor that it can consume polynomial amount of time. If this can be done, if we can make the translation of P1 to P2, means the construct block, if that execution can be done in polynomial amount of time, then only we can prove that P1 is also in P, since P2 is also in P, right? So let us see if we can assume that, or rather if translation, if this kind of situation occurs, if translation takes order of m to the power j instead of 2 to the power m, so m to the power j, if j is any constant, you can see it can be done in polynomial amount of time, right? So if the translation can be done in polynomial amount of time, then the output instance of P2 cannot be longer than the number of steps taken, that is it is at most c into m to the power j. Since this translation is can be done in polynomial amount of time, again whenever means output instance of P2, whatever the P2 will give the output, means P2 is being fed from the construct block only, so whatever the output it is going to give, it will be at most, means in the order of m to the power j only, but we have kept one constant because without if we have to represent it in terms of any factor, so it will be like c into m to the power j, where c is any constant. Now we can prove that P2 is in P, then so P1, because if this condition occurs, if only this condition occurs that the translation time is a polynomial amount of time, then we can come to the conclusion that if P2 is a polynomial amount of time it is consuming, then P1 will consume the same thing. Now let us see why we are claiming so. Now suppose that we can decide the membership of P2 on a string of length n, that is, it is we have already assumed this one, that it is consuming order of n to the power k. It's a polynomial growth for P2. Now then we can decide the membership of P1 on a string of length m in time What? Because previously we have seen the translation algorithm is consuming m to the power j. Fine. Now if P2 is fed with c m to the power j number of inputs, so since it is consuming order of n to the power k number of means if the complexity of decision algorithm of P2 is order of n to the power k, so here n's value is nothing but c m to the power j. So we have just put n equals to c m to the power j, and the total will be like c m to the power j whole to the power k. So if we have to you can see here, so both the terms we have successfully reduced to polynomial growth, and this is possible because we have if the condition is such that the construction algorithm can consume polynomial amount of times. Okay, so if we simplify the equation, it would be like order of m to the power j c m to the power jk, and you can see if c, j and k all are constants, so we can see that it can be done in polynomial amount of time, and we can conclude that okay, if P2 can be done in polynomial amount of time, because we have assumed it to be executed in order of n to the power k, that's why it's a polynomial, it is consuming polynomial amount of time. And if the construction algorithm, if we can design any construction algorithm which can consume polynomial amount of time for mapping the instances of P1 to P2, then the total thing can be like this, that since P2 is executing in polynomial amount of time, and again construction algorithm is also executing in polynomial amount of time, so the total decision can be taken in polynomial amount of time. That means we can reduce P1, which was previously a NP class, means which not NP class, which a problem which cannot be solved in polynomial amount of time, we can reduce that problem using P2, and that too can be solved in polynomial amount of time, right? Thus in the theory of intractability we shall use polynomial time reductions only. So in this concept, in this approach, we can reduce NP, that is P, that is which is not in P, and using a problem P2 which is in P, and we can use this polynomial time reduction. So previously P1 was taking exponential time to execute. Now if we can reduce it using P2, then it can be done in polynomial amount of time only, right? So as a consequence, the P2 instance will be of length, that is polynomial length of the P1 instance, right? Because we have successfully constructed construct algorithm or construct which can execute in polynomial amount of time. So in this fashion we can use this very important concept, it is polynomial time reduction. So far we have seen P class problems, NP class problems, and again we have seen this polynomial time reduction concept. This much for today, and in the next class we will see one more topic which are called NP complete problems. Thank you.